I am a senior at Colorado College. I did my work with the fabulous Adele Plunkett, who helped me greatly through the internship over the summer and more recently. So I'm looking at molecular outflows, but to understand those, we need to have a basic idea of star formation. So stars begin to form in somewhat dense clouds of matter, and these are known as stellar nurseries. And these are high in H2, showing up reddish pink sometimes when observed. But the important thing is that these densities allow for the matter to gravitationally attract other bits of matter, creating protostars. So there are three big parts of protostars: the envelope, the disk, and the protostar itself. So the envelope is surrounding the entire area. This is the denser than interstellar densities, but not as dense as the disk or the protostar, which are much more central. The protostar is actually within the disk. An important point to recognize for stars is that they must obey hydrostatic equilibrium, which means the pressure inside pushing out from the matter that constitutes the star is equaling the gravitational force that is trying to compress the star. So the star is not changing in size. And once a protostar eventually starts burning hydrogen in its core, that is officially when it goes from being a protostar to being a star. So here is a brief overview of the life cycle of a protostar, becoming these different classes, gaining, as we can see in the vertical columns, these outflows. And that is the focus of our talk here. So we specifically focused on the outflows. So what is an outflow? An outflow is jets of matter and entrained material that are being shot off of a protostar. The reason this happens is slightly beyond the scope of this talk, but at its base is to remove angular momentum from the system so more matter can be accreted onto the protostar. And this matter accretion is extremely difficult for us to track because it's happening within the envelope and going from the disk to the protostar. So that's why we look at the outflows to measure the accretion of matter rates, because we know that they're proportional. And importantly, we have to take into consideration the orientation of the system. That means if these outflows are pointed in the plane of the sky or possibly directly towards or away from us. So here we have an example. This is a mock-up of what would happen if you had a red-shifted jet outflow pointing away and then a blue shifted pointing somewhat towards you, but neither are completely in the plane of the sky or pointing towards you. Here, I tried to show if we had those two extremes, and we can see how these two different images would give us very different ideas of what these outflows actually look like, because we're just seeing the projection of them onto the plane of the sky. So transverse velocity is across the sky, and they, sorry, let me rephrase. The only way to get accurate information about transverse velocity is by tracking the outflow over a large time period, because you aren't getting any velocity component towards you. So when taking these molecular line measurements, you can't get the information there. So now we go on to tracers. Tracers are the different molecules that are used to track different parts of this system. So, for example, the disk may have different molecules comprising it than a part of the outflow. And knowing this and the fact that we can only see these tracers at specific temperature and density conditions because we are looking at their transition lines. So, for example, spectral window 25 shows us the CO 2-to-1 transition line, but it's possible for us to see a different transition line of the same molecule. And that would let us know that there are different temperature or density conditions in that part. So it gives us a lot of insight into these outflows. Here is the overview of all of the spectral lines we looked at. I will be focusing today mostly on 25 and 33. So here is what is known as a moment map. A moment map, this is a moment zero map to be specific, and it is showing the integrated intensity of light across a certain channel range. For this one, it's 352 to 593, centered on 8.1 kilometers per second. So the centered on 8.1 kilometers per second means the central source here is moving that fast. And the high and low velocity matter is referencing velocities high as in far away from this central velocity and low as in close to this central velocity. So this specific spectral window was quite complicated. So we decided to break it into separate ones. Looking at this elliptical region profile, so this is looking at the emission from spectral window 25, we see that there are separate peaks. So we would gain information from splitting it up like this into 6 different ones. So we have the first 3 blue shifted, and then we have the red shifted ones on 4, 5, and 6. Here, 3 and 4 are the low velocity, and 1 and 6, that 6 is meant to be on the other side, sorry about that, are the high velocity. And usually you see less high velocity emission because of the energy it takes to get the emission to that velocity. Now, red shifted and blue shifted, I haven't gone over the definition of that. Blue shifted is when light is traveling towards us, in this example, from the protostar. And red shifted is away from us. So we are still getting the emission from matter that is moving away from us. That is an important thing to realize. And that is how we get all of these maps. So here we have the very first one. This is low emission and very centralized, which makes sense because this is the high velocity map. So there isn't much emission, especially out in the further regions. And then as we go, you can see more of the outflow forming. These contour lines, the blue are multiples of 5 times the root mean square of the background noise. And the cyan is 3 times that. And 3 times the RMS is generally accepted as the lowest statistically valid contour line to draw. And now we have much more extended. Now we're seeing some northern outflow as well. And then onto the red shifted. So we see it's a bit, it looks like the red shifted is the northern outflow and blue shifted for the most part is the southern. And again, we're seeing much more low velocity emission than medium, which is still there, and even high. I would like to take a second to talk about this area. It is what we think is a protostar in the background of our field of view. So we didn't intentionally pick up this source, but it is showing up. And in order to remedy that, we might need to re-clean these images in the future to get a lower background noise and rule out for sure if that is emission from the protostar we are looking at or a background one. Now, this is spectral window 33. We decided not to split up the emission because of the spectral profile, but even looking here, you can see it's mostly contained around the protostar and the protostellar disk. We see some outflow going below and above, particularly in the purple line, which is 3 times the root mean square, but redshifted. And here is why we didn't break it up. This shows that most of the emission is centralized around between 286 and 167, those channels. So we wouldn't gain anything from creating separate moment maps of them. Now, our final goal here is to fit Gaussians, 2D Gaussians to be specific, to these data. This step, the point of this is to have a quantitative way of describing these different clouds in order to track them over time and compare to others. Here is the example we chose because 33, as we saw, is very central, so it's much easier to fit a Gaussian to it than others. And it gives us these parameters which we can track the change in the parameters over time. Many others will need more complex fits, maybe not only Gaussians, maybe more than one Gaussian, but we will continue fitting these Gaussians to the rest of the moment maps. And once that is done, we will use those Gaussians to determine the size of the emitting region for each of the molecules. We will use this information to compare to the data taken by Adele et al. In 2015. And as I said, we will reclean these images because it will help with that possible background protostar as well as any other uncertainties. I would like to shout out my advisor, Natalie Gosnell, my best friend through this, Savannah Woods, and my mentor, Adele Plunkett.
Great job, Casey. Great job.
Thank you.
Did anybody have a couple of questions for Casey? We have one from Andrew Baker.
Hi, Casey. Nice talk. I'm an extragalactic astronomer, so my knowledge of star-forming regions is not very extensive. Could you just say a little bit about the source that you were observing, how it was, first identified, and why it was decided, to make these observations?
Yeah, definitely. This source, it's called Carma 7. It's in the Serpens South cluster, and it is specifically important to outflow research because it shows this bipolar outflow that in theory we should be seeing most of the time, if not all, but in practice is very hard to find a good example of. So this is the prototypical bipolar outflow example that we have at the moment.
Cool, thank you.
This was a really good talk, Casey. Thank you so much for telling us about star-forming regions. This is really awesome.